Okay, welcome to the third day for gas laws and advanced chemistry. So we're going to talk about a bunch of different things today. Actually, we're not really talking about that much today. What am I talking about? I'm going to introduce the difference between ideal and real gases kind of quickly. We're going to do a couple of calculations involving moles and molecules and not just pressure, volume, and temperature. And we'll discuss briefly the departures from ideal behavior of gases. In other words, when these things don't necessarily behave ideally, what do we do with these calculations? And I'll kind of explain. So, ideal gases. Now, we talked a little bit about this already, but ideal gases are gases that that are behaving exactly as we want them to. Real gases are placed in uncontrolled environments. You know, the temperature, pressure, and volumes are going to be manipulated or changed, and under those conditions, gases are not going to behave the way they're supposed to. However, what we're going to do is we're going to treat all of them as ideal. Now, these things don't really exist, as I explained before. Gases that are real can be liquefied. You know, they can condense and turn into a liquid. They can deposit and undergo deposition and produce solids in the case of like carbon dioxide. But gases will behave ideally at very high temperatures. Oh, need to use the pen here, Colin. At very high temperatures and really low pressures. And so that's what we're going to focus on. And you can remember this because you know you're going to be asked questions over this, right? Is how do I remember that they, high temperatures, low pressure? Well, very low pressure, they're very spread apart. Gases are far apart from one another. And at really high temperatures, they're moving really quickly, so they don't have enough time to attract to one another. And so, yeah, like I said, high temperature and low pressure. Now, one way to remember this, and it works really well, is just like you guys in the summer. So in the summer, you guys are most ideal, right? That's your happy time. There's really high temperature in the summer, and you're under really low pressure. So if that helps for you, you're welcome to use that. If not, you can just remember they need to be far apart and move fast. But yeah, high temperature, low pressure. So this is the ideal gas law. At CONSOL, we call it PUVNERT. I have heard teachers from other districts refer to it as PIVNERT. It doesn't really make any difference, but it is the pressure times the volume equals the number of moles times R, which is universal gas constant, times the temperature in kelvins. The universal gas constant, though, that numerical value, you need to know it, and you must know the units, because in order to use that, you can change the universal gas constant to whatever you want in terms of units, but it remains the same, and it's a whole lot easier just to remember one of them and to change everything to those units. And I'm writing the units up here on the top, but they're already down there on the bottom. But I always say LATM molk in the denominator. So LATM on top and MOLK in the denominator. That'll help you remember that you need to change volume to liters, pressure to atmospheres. Moles have to be, of course, in moles. And your temperature needs to be in kelvins. So we'll do a couple of examples of this. I do want you to try a couple of these on your own, but we'll see how it goes. Okay, so... Sorry, I'm a little under the weather. All right, so a 5-liter flask contains 0.6 grams of O2 at a temperature of 22 degrees C. What is the pressure in atmospheres inside that flask? So in this unit, because we're using so many variables, it's a great idea to just go ahead and list them all. And the first thing they're actually giving us is grams. Actually, the first thing they give us is volume. We could do that really quickly. Let's see. The volume was 5.0 liters. The other thing they're giving us is grams. That's how we're going to solve for the number of moles. What we don't know here are the number of moles, but they did give us 0.60 grams of O2. You guys should know how to change that to moles. Real quickly, the molar mass of O2 is 32.00 grams. If I change that to moles, I'll get the number of moles that I need here. And that amount is, and I'm going to write it kind of underneath here. It's messy. Whoop, down here. 0.01875. Let me fix that. There we go. 0.01875 moles of O2. So now I know the number of moles. I need to know the temperature as well. They gave it to us at 22 degrees C, but we need to change that by adding 273 to get 295 K. And the overall, what we're looking for in solving this problem is the pressure. So And it says in atmospheres, which is great, because if we use our R value, which I'll write here as well, as one of our variables that we're actually given, which you would have to know, 0.0821, and then, of course, liter, atmosphere, moles, and Kelvin, we can plug in and solve. Now, this formula is PV, PUVnert. PV equals nRT, and what we're solving for is pressure. So what I'm going to do is take the volume and put it down here on the bottom. So my pressure equals nRT over V. So I plug in my number of moles, 0.01875. And actually, you really want to use the entire number that you got in the calculator. So really, 0.6 divided by 32 would be a better thing to plug in for the N value. And then your R and your T, of course, divide by volume. And I'll show you the prettier version of this. Yeah, there it is down there on the bottom. So all plugged in down here on the bottom. I would use the entire number that you get, 0.01875. And times your R, times your temperature, divided by 5 liters, and you'll get your atmospheres or your pressure that you were looking for. Pretty straightforward questions, very much like what we had before, but as you can see, we've got grams involved there, which you have to change to moles. So you realize that if we solve for moles, we may have to solve for atoms or molecules or whatever. And that's when the gas laws become a little bit more complex, depending on what they ask you, and having to do unit conversions for several different things. Other than that, it's plug and play algebra. So let's do another one. And this one, maybe I can get you guys to do a little bit on your own. But it says, how many grams of krypton are present in a 600 milliliter container? Okay, so they give us a volume of 600 milliliters. At 1010 degrees C, so they're giving me a temperature of 10 degrees Celsius, in which the pressure of the krypton is, so they're giving me the pressure as well, at 10.0 atmospheres. And what they're asking for is, it says, which pressure is 10 atmospheres? How many atoms is this? Does it not also ask how many grams is it? Oh, I guess it didn't, did it? It asked for how many grams. Oh, it did. No, it's at the beginning. It said how many grams. So what we want to know is, we want to know the mass in grams. And we also want to know at the end how many atoms. So there's two parts to this. To get mass in grams and mass in atoms, what I'm going to have to do is solve for the number of moles. Once I know the number of moles, I can then go find mass and go find atoms. So what this is, of course, is a PUVnert problem. PV equals nRT. And you're going to need to go and solve for moles first. So why don't you guys give this, I kind of dissected it for you and showed you where to go. Try the rest of this one on your own. Press pause, give it a shot, and then come back in a minute and I'll show you the rest. Okay, so I'm assuming that you actually went and tried the problem on your own. The number of moles in terms of the formula would be PV over RT. So what I would do is plug those in. I've got 10 for my pressure. My volume you had to change to liters, so 0.600 liters. And then in the denominator, the R value is 0.0821. Liter, atmosphere, mole, and Kelvin. So I'll need to change that temperature of 1010 degrees C to kelvins. And that ends up being like 1283. And if I plug that in, I end up getting my number of moles. Now, you'd want to use this entire number, of course. I think the number of moles ends up being 0.05696 moles of krypton. But you want the entire number that they gave you in the calculator. I'm just kind of rounding it a little bit here. If I took that number of moles, I could change to grams very easily. 0.05696 moles of krypton. Just look up what the molar mass of krypton is. And it is about 83.8. And you can solve for your number of grams, which in this case is 4.77. The other thing that they asked us to solve for, hopefully you did, was the number of atoms. So 0.05696 moles once again. And I know you guys are aware of this. In order to solve for the number of atoms, you would merely use Avogadro's number, which is 6.02 times 10 to the 23rd atoms of krypton. And you get your answer there, 3.43 times 10 to the 22nd atoms of krypton. krypton, yeah. Yeah, 3.43 times 10 to the 22nd. That's kind of how those problems are. Little bit of conversions here and there. You got to realize what you're solving for. If it's atoms or grams, definitely, or molecules, you're definitely going to have to go to moles first. So use your PubNerd to find moles. Here's a pretty version of the same thing. Yay, same answers. Okay. So there is some departure from gas laws, which I've kind of talked about before and talked about a little bit in this video as well. But gases, like I said, do behave most ideally at that high temperature and, of course, at low pressure. At high temperatures, the molecules are moving too fast to have attraction for each other. And at low pressure, that means really high volume. It means that they're going to be really farther apart. And so they're not going to have that attraction for each other. The higher the temperature, the quicker the movement, the higher that kinetic energy. So they won't have time to kind of interact with one another. And if they're really far apart, of course, the same is true. But there are ways to calculate when you take the intermolecular forces into account. And this is the actual ideal gas law, a more complex version. This is called the van der Waals equation, and it's really what, see, this is our pressure, volume, and over here, the same in RT. It's the same, except there are specific constants for each gas. This is the adjustment factors for A for pressure and B for volume. We're not actually going to do any of this. This is just for your information. We don't do it in AP chemistry either. There was a time, yes, when that was calculated, but no longer. We'll just treat things as though they were ideal. But if you had like water molecules with hydrogen bonding, there would be a number associated, an adjustment factor, for both the volume and the pressure for those water molecules. But again, we're not going to cover that at this level anyway, so that's fine. And last thing, departures from the gas laws also, here's three molecules down here. The one that actually has the least amount of attraction between the molecules is this one over here on the right. If we label, now what we're talking about here are intermolecular forces. And you do have to know, hey, intermolecular forces that are strong are going to be polar compounds and hydrogen bonding, which water, of course, has hydrogen bonding. And so does ammonia. Ammonia also has hydrogen bonding. So these are going to have stronger attractions to each other. Methane, on the other hand, is nonpolar. It is nonpolar, and so it's just going to have LDFs. London dispersion forces are really weak, and so methane would be the most ideal of these three gases. So that will play, you guys will have questions over that. Gases that have really high molecular masses and lots of polarizable electrons, really complex shapes, meaning they can't kind of bump into each other or whatever, or strong polar attractions, those are going to affect how ideal the gases are. And we'll have some questions over that, and we'll do some homework over it, but really you have to, intermolecular forces, we're not going to do any calculations with them, but you do have to understand which ones would be most ideal based on that behavior. And we'll pick up with mixing gases together and kind of what happens in terms of Dalton's law and partial pressures of different gases kind of in the same container, and their speeds, velocities, and kind of how they behave in the next unit, or in the next video. All right, that's all for now. See you guys later. So I think we're going to, yay, okay, so we're going to stop there.